Today we're going to build a simple URL shortener using Rust and the Oxum Web Framework. Think of it like Bitly, but much simpler and built by us. First, create a new Rust project. Edit cargo.toml and add these dependencies. Now let's set up the web server. In main.rs, first we bring in the necessary crates. Oxum is our web framework, handling routing and requests. CERD helps us serialize and deserialize data, which is useful when dealing with JSON. Then we import the HashMap struct from the standard libraries collections module, which acts as our in-memory database for now. We also import socket address from the standard libraries net module and arc from the standard libraries sync module. Tokio is our runtime for asynchronous operations, crucial for performance. A mutex is a synchronization primitive that allows only one thread to access a shared resource at a time. The TCP listener allows our server to listen for incoming TCP connections on a specific port. UUID generates unique identifiers for our shortened URLs. Now let's dive into the main function, the entry point of our program. First, we see Tokio main. This is a macro that sets up the Tokio runtime. Tokio is what allows us to write asynchronous code in Rust. Inside the main function, the first thing we do is create our database. We're creating a hash map. This hash map will hold our short IDs and the corresponding original URLs. It's wrapped in a mutex to prevent data races. A mutex acts like a lock. Only one thread can hold the lock and access the hash map at a time. This prevents chaos if two requests try to modify the database simultaneously. Finally, we wrap the mutex in an arc. ARC stands for Atomically Reference Counted. This allows us to share the database safely across multiple threads. Because our web server will handle multiple requests concurrently, we need this to allow different parts of our code to access the same database. Next, we define our routes using Oxum, router, new. The router is what defines the different routes our server handles. We use the .route method to define each route. We have 3 routes, the root path /, which will display a welcome message, shorten, which handles post requests to shorten URLs, and ID, which handles get requests to redirect users to the original URL. The ID part is a path parameter, meaning it can be anything after the slash, like /ABC123. After defining the routes, we use with state to share our database with all the routes. This makes the database accessible to our handler functions, homepage, shorten URL, and redirect URL. Then, we define the address our server will listen on using socket address. 127.0.0.1 is the local loopback address, and 3000 is the port number. So, our server will be accessible at port 3000. We create a TCP listener to listen for incoming connections on that address. The await keyword is crucial here. It means this operation is asynchronous and won't block the main thread. Bind is an asynchronous operation. Bind function returns a result, which means it can either succeed or fail. It might fail if, for example, the port is already in use by another program. Unwrap is a way to say, I'm pretty sure this is going to work, and if it doesn't, just crash the program. We print a message to the console to let us know the server is running. Finally, we start the server using Oxum, serve. The serve function starts the Oxum server, listening for incoming requests on the specified listener and using the routes we defined in the app router. Again, await is used because serving the requests is an asynchronous operation. The unwrap handles any potential errors during server startup. So, that's the main function. It sets up the Tokio runtime, creates the database, defines the routes, starts the server, and begins listening for incoming requests. It's the control center of our little URL shortener. Now let's look at the homepage function. It's super simple, it just returns a string. Welcome to the Rust URL shortener. Use post shorten to create short links. Okay, let's look at this struct, URL data. We define a new struct called URL data. It is going to hold information about a URL. Here, we have just one field, original URL, and its type will be string. We use a derive macro. It's like a little code generator that automatically implements certain traits for our struct. In this case, it's implementing the serialize and deserialize traits from the CERD crate. Alright, let's dissect the shorten URL function, the heart of our URL shortening logic. This function is what gets called when a user sends a post request to the shorten endpoint, providing the URL they want to shorten. It takes 2 arguments, and it returns a JSON response containing a hash map. This hash map will hold the shortened URL. Let's look at the arguments. State is an Oxum extractor that allows us to access shared state across our application. Remember, we used with state in our main function to provide the database. So, state DB extracts the database from the application state and makes it available to this function. The DB is our thread-safe, shared database. The second argument is JSON payload. This is how we get the URL that the user wants to shorten. JSON is another Oxum extractor that handles JSON data. It automatically deserializes the JSON request body into our URL data struct, which we defined earlier. So, payload will be an instance of URL data, and we can access the original URL using payload.originalURL. Inside the function, the first thing we do is generate a short ID. We use the UUID crate to generate a UUID, which is a universally unique identifier. We convert it to a string and then take the first 6 characters to create our short ID. This gives us a reasonably short and unique identifier. Next, we access our database. This is crucial. Because our database is shared across multiple threads, we need to lock it before we can modify it. db.lock.await acquires the lock. The await is important because acquiring the lock might involve waiting if another thread is already using the database. We have to make this db variable mutable because we are going to modify the database. Now that we have the lock, we can insert the short ID and the original URL into the database using db.insert. ShortID.clone creates a copy of the short ID because we'll use it later in the response. Finally, we construct the response. We create a new hash map to hold the response data. We insert a key called short_URL, and the value is the full shortened URL, which we construct using format. We then return the response as JSON. Oxum automatically serializes the hash map into JSON and sends it back to the client. So to recap, the shorten URL function receives the original URL as JSON, generates a short ID, stores the mapping in the database, and returns the shortened URL as JSON. It also uses asynchronous operations and proper locking to ensure data consistency and performance. Alright, let's explore the redirect URL function. This function is responsible for looking up the original URL in our database and redirecting the user to it. It takes 2 arguments, and it returns a result. A result in Rust is a way to handle either success or failure. In this case, it can either return a redirect if the URL is found, or a status code if it's not. Let's look at the arguments. Path ID extracts the short ID from the URL path. Remember, we define the route/ID in our main function. So if a user visits /abc123, ID will be the string abc123. Path is an Oxum extractor that helps us get path parameters. The second argument, state DB, is how we access our database, just like in the shorten URL function. It extracts the database from the application state. Inside the function, the first thing we do is access our database using db.lock.await. We lock the database to ensure we have exclusive access. This is important because we don't want another thread modifying the database while we're trying to read from it. We use db.get to look up the original URL associated with the short ID. db.get returns an option, which can be either some value, if the key is found, or none if it's not. If the URL is found, it's assigned to the URL variable inside the if block. If the URL is found, we create a redirect response. Redirect. Temporary creates a redirect response that tells the browser to go to the original URL. OK wraps the redirect in a result, indicating success. If the URL is not found, the none case, we return a not found error. Status code. Not found represents the 404 HTTP status code. Error wraps the status code in a result, indicating failure. So to summarize, the redirect URL function takes the short ID from the URL path, looks up the original URL in the database, and either redirects the user to the original URL if it's found, or returns a 404 not found error if it's not. It also uses asynchronous operations and locking to ensure data consistency. So, that's the basic structure of our URL shortener. We've got routes for shortening and redirecting, a database to store the mappings, and asynchronous handling to keep things fast. Of course, this is a simplified version. A real-world URL shortener would need a more robust database, perhaps a proper one like Postgres or Redis, error handling, input validation, and probably a nicer user interface. But this gives you a solid foundation to build upon. It is time to start the server and test it. Run this command in your terminal, cargo run. We can see our server is running on this URL. If we open this URL in the browser, we can see the message. Welcome to the Rust URL shortener. Use post shorten to create short links. Now let's test the post requests in Postman. Create a post request with shorten route URL and set the original URL in JSON body. Send the request and you will see short URL in response. We can see the ID in the URL we get in the response. If we copy this ID and send the GET request on /ID route, here in Postman we can see the HTML file in response. If we visit this URL in the browser, we will be redirected to the original URL. And that's it. We just built a URL shortener with Rust and Oxum. If you found this tutorial useful, check out other quick coding challenges on this channel, and comment below on what you'd like to build next. See you in the next video.